Hello, today we are going to go over two proofs. The first proof will be a proof by mathematical induction, and the second will be a proof by contradiction. So our first proof says that we need to prove that n times the quantity n plus 1 all over 2 is equal to the sum of all k's from k equals 1 up to n for all the natural numbers. So we're going to let P of n be the proposition stated above. The first step in mathematical induction is to show that P of 1, or the base step, is true. So plugging in 1 for n in our proposition, we show that both sides of the equation equal 1, and this step holds. The next step is the inductive step, and we're going to first assume that P of k is true. And using this assumption, we're going to show that P of k plus 1 is true. So again, our assumption, P of k, is 1 plus 2 plus 3 all the way up to k, is going to be equal to k times the quantity k plus 1 all over 2. So this is our assumption. We're going to assume that this is true, and we're going to need to prove, we're going to show that P of k plus 1 is true. So if our P of n is true for some k, and we can show that it's true for some k plus 1, then we've shown that our P of n is true for all the natural numbers. So again, using our P of k, we're going to add k plus 1 to both sides of our P of k statement here. And if we do that, we get this here. So again, it's 1 plus 2 plus 3 all the way up to k, but then we added a k plus 1 to the left-hand side. And this is the right-hand side of our P of k. And again, we just added the k plus 1. So if we do a little bit of algebra, we end up with this statement right here, and we see that this statement on the right-hand side is equal to the right-hand side of our P of k plus 1 statement right here. And the left-hand side here is exactly the left-hand side of our P of k plus 1 statement here. And so we use the assumption that P of k is true, and we use that to show that P of k plus 1 is true. So therefore, if we assume that P of k is true, then P of k plus 1 is true, and by the principle of mathematical induction, P of n is true for all the natural numbers. For our next proof, we are asked to show that there is no rational solution to the equation x cubed plus x plus 1 equals 0. So we're going to assume the contrary. We're going to prove this statement by contradiction. So we're going to assume to the contrary that there is, in fact, a rational solution to this equation. So we're going to let x equal p over q, which is rational, where p and q are elements of the real numbers, and p over q is in its most reduced form. So we go ahead and plug in p over q into our equation, and we have p cubed over q cubed plus p over q plus 1 equals 0. And multiplying through the entire thing by q cubed, we get this statement, which we called equation 1. And we're going to look over 4 cases for this equation. So in this first equation, the first case we're going to consider is if P is odd and Q is even, then the left-hand side is going to be odd. But 0 is not odd, which leaves us with a contradiction. The second case is if Q is odd and P is even, then the left-hand side will again be odd, and again we have the same contradiction. The third case is if both P and Q are odd, we will again end up with an odd value on the left-hand side, and once more we have the same contradiction. And the fourth case that we're going to consider is if both P and Q are even, then P over Q is not in its most reduced form, which is not possible because we assumed in the beginning that it was in its most reduced form. So there's no case in our equation that does not lead to a contradiction. So therefore, we can conclude that there is in fact no rational solution to the equation x cubed plus x plus 1 equals 0. Thank you for watching.